All right, welcome everybody to Hands-on Machine Learning Engineering and Operations. Welcome to this last module of the course. It's going to be on experimentation. And we now have a full machine learning system that is deployed and that is running end-to-end. We now have a model that is deployed in production. We have deployed it on Google Cloud so that it can serve prediction to whoever wants to use it, basically. And we have everything we need. We have all the pipelines that we need to be able to constantly improve on this model and retrain it and keep making it better at the end of the day. And naturally, two questions are still unanswered. The first question is, can we constantly monitor that in real life, in the real world, whenever we ship a new model, that we are only shipping models that are producing better performance than the previous models? This is outside of the MLflow environment. This is having different models running in the real world and comparing the real life performances of these models. And this is exactly where experimentation is very useful. And then the second question that we want to ask is, can we deploy a pipeline or something that constantly monitor the performance of this model in the lab with the new data that's being generated, and that tells us in some way whether we have some kind of model drifting, whether we have some unnatural decrease of performance that probably comes from the fact that maybe the underlying data is changing. Maybe people are getting better at this game, and maybe people are changing the way that they play, and therefore maybe the model that has been trained on a specific set of data, maybe the model is not reacting well to people becoming better. This is definitely something that could happen for a game like Belote Manier. Another reason why the model might be decaying in the real world, as we saw last time, is because maybe a recommendation engine would become worse because consumer preferences are changing. People watching TikTok or whatever start liking or disliking certain type of video, and the model cannot be automatically improved if it doesn't retrain on newer data that reflects better the new customer trends. And so here we're going to be answering these two questions in this module. We're first going to talk about experimentation, and you'll see it's going to be pretty short, but we're going to try to get a lot done by looking at some experimentation data and making some decision based on this data. And then the second thing that we're going to do is we're going to look at the last assignment number 6, which is going to be on Airflow. And this lab or this assignment is going to show us how to deploy an ETL, so an extract, transform, and load pipeline that is going to be scheduled through Airflow, and that is constantly going to pull some data and do some reevaluation on this data. So I hope that you guys are pretty excited. Let's get into it. So first of all, talking about experimentation, there is a lot of way to do experimentation, and in fact, you can spend your whole life building experimentation frameworks for whatever problem space that you're working in. Here we're going to do something very simple, but keep in mind that it can be basically as complex as you want. For us, in the interest of pragmatism, we're just going to load a few libraries here that are going to be important. In fact, actually, I should have started from here, where I load the general libraries of the course, I display the option, and I load, as always, the base path. Again, just make sure that this base path here is pointing to the location where you are storing the data for this course. This is where you have loaded the material and where you're storing it. And today we're going to be very interested in this experimentation.csv. This is the file that we're going to be using here to compare the performance that two different models are generating in real life. We are going to make a decision based on this data that we're observing here. So first of all, we're going to load this data, and we're going to look at the data that we're dealing with here. And essentially, what we're dealing with here is two models. We're dealing with model number 1, or like random forest version 1, and model number 2, random forest number 2. And essentially, what we have here is we have 200,000 rows of data, 200,000 samples, that tells us how well the model is performing in the real world. Not in the sense of what is its accuracy or what is its ROC or precision score or whatever. Like literally just how much points this model on average playing against real people, how much point this model is generating. That's the question here that we're answering with this data. And why do we want to know that? Because now we're outside of the lab. We don't care about accuracy anymore. We don't care about all that kind of stuff. The only thing we care about is how well is our model performing, how much is it crushing basically people who try to play against him. And the reason why we want to do that is we want to compare whether version number 1 is performing better than version number 2 in real life. And this is interesting because if we believe that we have in version number 2 a model that's supposed to be performing better, then we would want him to generate more average points as it's released in the real world. And this is exactly what we're going to be comparing with our experimentation framework here. So essentially what we're going to do is we're going to grab this data and we're going to pass it to our data frame here, experimentation df. We're just going to rename a few things. We're going to take this model column and we're going to capitalize it. We're going to do the same with the contract and we're going to do the same with the reward. It's a very small detail, but it's just going to be nicer when we plot the graph. And essentially what we want to look at is we want to look at a graph that tells us which model is performing better, but not just which model is performing better, which model is performing better in a statistical significant way, in a way that basically tells us that we have enough data samples to confidently accept the hypothesis that one of the model is performing better than the other one. And this is exactly what we're going to do here with our graphing here. If we use this library that's called Seaborn and can plot how well each model is performing overall, what we can do is we can create a Seaborn bar plot that's going to compare how model number 1 is performing versus model number 2. And we're going to look across the average of all of the hands that it has played. And we're going to look at the average reward that each model is generating in the real world. And if you're wondering where do we get this data right now is artificially generated just to illustrate the point that we're making. But we actually do have a pipeline that gathers all of the hands that are played by real players who log onto the Belote Mania game. We basically have a pipeline that collects all of the real games that are played, and we consistently check different versions of different models so that we actually do exactly this. We actually do check which model is performing better in the real world. So even though this specific data is artificially generated, we do have the real data somewhere. It was just easier to get it ready like this. So that's a small side note. But essentially what we're going to do now is we're going to create a bar plot. We're going to pass it the experimentation df, which is the data itself, a few minor tweaks, let's say, in the way that we name things. And then here what we're going to do is we're going to say, hey, please just plot the different models and just look at the average reward generated for each of these models over the whole sample size. And something very important that we're going to do, and that's why Seaborn is so great for that, is we're going to generate a bootstrapping here of our samples so that we can create a confidence interval around the mean, and we can look whether we can exclude the hypothesis that they are the same or that they are different based on this confidence interval. This is exactly what we need so that we can confidently just say that they are more or less generating the same value, that one is performing better than the other one, and stuff like this. If you don't really understand how bootstrapping works, I definitely recommend for you guys to check it out. I put a note in the useful resources with some guy who just explains stuff very, very well. And so you can definitely check it out on YouTube. He's going to explain much better than me like how bootstrapping works. But essentially, bootstrapping is going to allow us to create a confidence interval around the mean, and that's going to allow us to confidently accept or reject some hypothesis. And we're going to set the bootstrapping to 5,000 here, and that's it. There's nothing else needed. Just run the plot, and let's see what happens. All right, so if we look at our models here, version 1 and version 2. Version 2, talking with the data scientists in the team, version 2 was supposed to be the better model. That's actually why it got released in production, so that we could really see whether it would perform in the real world better. And if we look at the two graphs here, we do see that the average number of points is extremely similar. In fact, version 2 is generating on average a very small amount of points that is lower. Overall, it's completely positive. So overall, the computer generates a positive amount of reward. It's probably because it's performing better than any human at this game. But between the two versions of the model, looking at the confidence interval around the mean, we definitely cannot accept the hypothesis that version number 2 is performing better than version number 1. In fact, it's performing slightly worse with no clear statistically significant evidence that it's performing worse than version 1. That's very, very interesting. But even more interesting than this is this holding up for all of the different contracts that we have. Essentially, different contracts are different versions of the game, different rules of the game. So it could be very interesting to generate the same picture here, but really to break it down by the different contracts that you have at Belote-Manier. And we would see quickly whether this failure to reject the hypothesis that version number 2 is performing better, we would see whether this holds when you break down at the contract level. Or if maybe at some contract, maybe version number 2 would perform better. And this is exactly why we go to the next graph here. And this is why we look at the same bar plot, the same graph basically, providing it the same data. But now we're gonna look at different contracts. So we're gonna look at different contract here, which is why we pass it as the X variable. We're still gonna look at the mean value of the reward for each of the different models. And now we're gonna provide this QA separation here at the model level so that we can see how the different models perform for different contracts. And I'm just going to run this. It's again with the same bootstrapping, 5,000 samples. So again, please do check how bootstrapping works and why it's important to understand it. This is exactly what we need to be able to construct the confidence interval. So make sure that you understand what's going on here. And essentially now what we're having here is a very, very different and very interesting picture of what's going on in the real world. So it seems that in the real world, for most of the contract, we have a slightly different picture. It seems that for some of the contract, like Tutatu, Diamond, and Clubs, version number 2 is performing better for some reason. We don't really know why, but we just know that it seems to be performing better. Now, the only contract for which version number 2 is actually performing better is for Clubs. This is where we have a confidence interval that's not overlapping the true mean value of the reward, which could be anywhere in this confidence interval for version number 2, is outside the bounds of the true mean value of version number 1 here. That could be anywhere in here. The true mean value of the reward could be anywhere in this confidence interval. That's exactly the reason why we built a confidence interval in the first place. And we see that it's overlapping for all of these guys except for Clubs. So maybe there is a reason why version number 2 is clearly performing better at Clubs, but for all the rest, it's definitely not conclusively working better. So maybe when we play Clubs, good, interesting decision to take here would be to kind of like have a bit of logic in the backend that would implement switching logic that says, hey, if the player decides to play at Clubs, use the AI that's just smarter when we play at Clubs. So just use this AI here that is called random forest version number 2. But essentially, more than the decision making to really take for Belote-Manier, what I really wanted to show you is how I think about experimentation and how I think about grabbing some experimental data that comes from the real world and really studying it in a statistical setting so that you can make better decisions. All right, now that we understand what the fundamental A/B testing framework would look like if we were to deploy it for our use case, we can move on to the multi-arm Bandit as the system that we could use to deploy different models continuously based on their performance in the real world. And just a small note on this, obviously today we're not going to get into a very deep down development of the framework. There is a huge amount of material out there that you can find, and well, based on the feedback that I get on this specific section here, I might push a little bit and try to really develop the framework specifically for the use case that we have here. But essentially what I really want to make sure that you have is an understanding of the fundamental mechanics of how multi-arm Bandit works and how it can be leveraged for our use case. Well, if you have read some of the articles that I wrote about the way that I actually built the AI itself for the main game, not the contract phase, I leveraged a technique, let's say a field of development called reinforcement learning, right? And it should come at no surprise if you find some similarity between what I describe in my blog post here about training a reinforcement learning model to beat myself at my own game, and how I talk about like the way that reinforcement learning, let's say, a proper framework to train an agent to observe what's going on in an environment and to take action based on this environment and the reward that it takes. What we're doing here with multi-arm bandit experimentation for the contract phase is very similar to what we do here with reinforcement learning for the main game. I don't want to add too much complexity to this, but essentially I think of multi-arm bandit as a simplified version of a pure reinforcement learning framework, where instead of observing the rewards many steps in the future by taking an action now, you actually observe the reward directly. You take an action, you observe the reward, and you move on, you take another action. In reinforcement learning, and what you're going to read about here, it's the other way around. Like you take an action, well, actually you take several actions, and then some way further down the road, you get a reward. So here today, we're going to talk about the foundations of how this system would look like in practice for us as we roll out of our models. And it all starts with, let's say, two classes that we need to create, right? At its most simple and fundamental core, the first thing that we're going to have is an environment class, which is going to basically, let's say, tell the agent how the environment around it behaves when it takes actions in it, right? And this is going to be very useful because this is going to be what the agent uses to directionally know whether it is doing some good or bad things. And so obviously it comes at no surprise that the second class that we're going to need is an agent. And we're going to think as an agent as a way to deploy the different models that we have available for us, right? Our models and their deployment are just two specific actions that we can take. This is exactly what we want. We want to be able to let our agent take some actions, and then based on these actions, we want basically these actions to have their implications or to reverberate in the real world, in the environment, so that it changes the environment that the agent is in, and so that the agent needs to adapt once again to the new conditions of the environment surrounding it. And so the way that this is going to work is that we're going to define two methods in our environment here. We're going to define a method where, let's say, the environment applies the action that the agent takes, and it provides some reward to the agent based on behavioral change that the agent gets from this. I'm going to get back to that later, but this is what we're going to define here in the environment. And in the agent, we're going to define a bunch of different things. We're first going to define the actions that the agent can take. I'm going to get back to the epsilon because that's pretty important. That's going to be the main parameter for the algorithm that is underlying the whole system, the algorithm that is helping the agent decide whether to launch version number 1 or version model 2 of the model. We're going to define some reward. Think about this reward here as some kind of like table or some kind of like hard memory that the agent basically continuously updates, right? It's a memory that tells the agent like, hey, when I applied this action number 1, I usually tend to observe this kind of reward. When I applied action number 2, I usually tend to observe this other kind of reward. So it's kind of like this memory, like very similar to the way that we handle the world as human. We take actions in the world and we remember like, hey, when I touched the plate, I burned myself. And so that was like a pretty hardcore negative reward that I got there from touching the plate. So this is going to be exactly the same thing here. We're going to define this reward. We're going to keep as a convenience also in our class what are the total number of actions that were taken and what is the total accumulated reward that the agent took over and over by deploying different models. And now it's time to get real, because what are we talking about really when we talk about rewards? In the context of our problem here, the reward that we're talking about here is the points that are generated or that are associated with each of the model. And so our agent, when it needs to make the decision as to whether it should deploy model 1 or 2, it actually observes the points that each of these models generate in the real world, and it keeps tracks of these points in its hard memory so that it knows which model it should roll out. Now, this is exactly the first variables that we need to define in our class so that we have everything instantiated properly, and everything from there is just a few methods that will dictate how the agent behave. And I usually like to think about, first of all, like an overall method that is composed of small steps or small actions. We're going to start looking at this take action here so that we're going to understand what do we mean when we talk about the agent taking an action. What we're talking about here is we're talking about the agent, first of all, doing some kind of evaluation of the epsilon that we define here. And I'm going to go back to that in a second. But first of all, we're doing some evaluation of this epsilon. And then based on some logic that we do in here, so there is a bit of logic here based on whether probability is higher or lower than the epsilon that we've defined. So we're just going to leave that aside for a second, but based on a bit of logic here that we're leaving aside for a second, we're doing two things. Either we're taking a random action or we're taking what is called an optimal action. And again, think about the example of buying a new oven, putting a plate in the oven and wondering whether you should buy a glove, right? If you touch the plate and you see that it's very, very hot, you should probably purchase a glove. But if you never touch the plate, you're probably going to buy the glove without touching it, and you're always going to be left wondering what would have happened if you had touched the plate. This is exactly the logic of exploitation versus experimentation. What we have here is, in most of the cases, or progressively as we go, we tend towards taking what is called the optimal action here. We tend towards deploying what is for us the best model, the model that is generating the biggest amount of points. And we tend to, little by little, stop taking these random actions, which for us basically mean deploying randomly one or the other model. So this is exactly what's going on here. The action that we take is based on some hyperparameter called epsilon here, which is a hyperparameter that defines whether we're going to be doing more exploration or exploitation. Based on this parameter here, we're going to take the optimal action or a random action. We're going to touch the plate randomly just to see what's going on and whether we really needed the glove in the first place, or we're just going to purchase the glove because it's the optimal action to take. It's the action that protects us from getting burned, like when we touch the oven. So this is what's going on here. And essentially, like once we have made the decision here, this line is critical because it simulates the decision that the agent takes. So once this happens and we took the action, essentially what we're going to do is we're going to leverage the instantiation of the environment that we have defined here. So we're going to pass the environment that we have created there as a, let's say, as a variable, as a parameter of our agent, so that the agent always knows what's going on in the environment that it lives in. And so what we're going to do is, once we have taken this action, we are going to apply a step. We're going to apply this action in this environment so that we're going to be able to observe the implication that it has. We're going to preserve this current action here, let's say, as the action that was decided in this round of playing or in this round of interaction. And that is it. That is what taking an action looks like. What we haven't talked about so far is what happens exactly when you take the optimal action or what happens when you take the random actions. When you take the random action, which is the simplest thing right now, what we do is a random action just gives us randomly a model 1 or a model 2. It just gives us at random like one of the two, and it's the one that's going to be deployed. Now, when we take an optimal action, what we actually do is we go drill down into our memory here. We go, first of all, like we iterate on each action that exists, that are registered, let's say, that are things that we know we can do. And what we do is we go deep down into our memory. Remember, like our memory of the world, our experience of how things work in the environment that we live in. And we see for this action, what is the reward that we have generated on average based on how many times we have applied this action here. And we put it in our estimates. And that is important because now that we have this estimate of how much reward we have, how much value we generate, how many points do we have when we deploy version 1 versus version 2. Now we can take the optimal action for us, just becomes just us picking the model, the actions, which is again a deployment of the model. So it becomes us picking the action that has the highest estimate, that is generating the highest reward based on the number of times that it was applied before. This is exactly what we call an optimal action in our context. This is the deployment of the optimal model. And so now the final step, or the last part of this pipeline here, is to understand, after you have applied a step, what happens? Well, after you have applied the steps, which again, if you go back to the environment here, is just a very simple function that just basically says like, hey, we are rolling out a new policy. And this is obviously a placeholder. This is why I said in the beginning that I'm trying to talk about the foundations here. I'm not going to get too much into the details, but what would happen here in this method in practice should be the code that actually takes, for instance, the name of the model as an input. That's what the action is. And for instance, launch a new deployment of the model on the cloud functions that you have in the real world, or just connect to wherever you have your stored models and roll it out through an MLflow script that puts it into production from staging. So that is exactly where the real stuff is happening. But for us, I just really want to focus on the experimentation framework itself. So for now, for us, this apply step, it doesn't do much. It just basically say that we are rolling out a new policy. And then later on, maybe the next day, maybe in the next week, whenever you believe that you have accumulated enough data to start observing how many points the deployed policy, the deployed model is generating, what will happen at some point is that as the agent, you will observe the reward from having launched this policy, right? Obviously, you need your current action to be positive. Well, not really positive, but to exist in the first place. If it doesn't exist, you cannot observe a reward associated with this action, right? Because it hasn't been executed. If it does exist, then you can move on to grab your environment and compute the reward from having deployed this action. And again, if you go back to the compute of the reward, this is again a very placeholder function. It has this very simple random generator of reward, random generator of value. Again, this would, in practice, come from having rolled out a new policy. So it would be something here, it would be some kind of ETL here that would grab, maybe query your BigQuery table, look at all the games that have been played since you launched the new policy, and see what is the average reward, the average number of points that the deployed model generating over the last week or over the last period where you have deployed this new policy. That's exactly how your reward would be computed in practice. For us, for now, it's enough to have, let's say, this random number generator that just provides us some kind of reward. And then essentially what we are going to have then is we're going to have the hard memory of our agent. Remember, we are here again, we are in the context of our agent. We're going to have the hard memory here, do some tracking, do some, let's say, bookkeeping of what is the reward that I have generated for my current action. And, just some kind of like incremental counter that tells me like, hey, by the way, you've applied this action again. And therefore, afterwards, when the time comes to take the optimal action, I have this function working here because it's been updated every time that I observed a new reward. All right, and after I have performed this hard memory tracking, what I do is I reset the current action to none because we have taken the action, we have observed the reward, and the loop ends, right? We're back to having to take a new action to observe some new reward in the future. So essentially, that's the whole pipeline, or like that's the whole framework. It looks pretty simple for now, but if you understand the main mechanics, it's already pretty important. So this is exactly what we're going to do. We're going to launch this framework by, first of all, instantiating an environment, instantiating an agent, and passing it the environment. Remember, this is what we do here. We pass the environment as a parameter of the system itself. And now what we're going to do is we're going to iterate 10 times. In each of these iterations, we're going to take an action. Remember, when we take an action, what we essentially do is we roll out a new policy in the real world. And then right after, we are going to observe the reward. Now, again, this is not very representative of what would happen in the real world, because in the real world, when we deploy a new model, we want people to start playing with this model. So what's going to happen is we're going to wait, we're going to give it time, we're going to let the model be played with enough, 1 day or 1 week, so that when we observe the reward, we are sure that we don't have too few samples on which to compute this average reward, this average number of points, right? But here, for simplicity, we're just going to compute this reward straight away. After this loop, we're going to print the hard memory of our agent. And why do we do that? We do that so that we can see how the agent thinks. Based on its accumulated knowledge of the world, we're going to see how the model behaves, what kind of models it deploys, and why it does so. Actually, I'm going to increase this a little bit. Well, I mean, we can start with 10 iteration and then move on afterwards. So here we go. Launching the system, we see that it takes 10 steps. The first one is a rolling out of model version 1. We give it a week, we observe the number of points, and then it rolls out model version 1 again and again. And then at some point, it moves on to model version 2. Now, by the time it has rolled out 3 times model version 1, probably model version 1 has accumulated positive reward. It is the optimal action just because model number 2 has never played in the real world. So essentially what we are here is we are in this phase where we take the optimal action and the agent just keeps going with the deployment of model number 1 over and over again. But at some point we can see that it decides to roll out model number 2 here, and that's probably because at some point the exploration phase of our system kicks in, and instead of just leveraging this optimal action over and over again with a specific probability here, it decides to take a random action, explore a little bit, check out what's going on if you roll out another model than the one that's considered optimal, and observe some kind of reward for this new model. Now you see that it goes again with model number 1, 1, 1, 1, 1, and then finally again an iteration of model version 2. And so if we look at the final hard memory of our model, we see that it will probably keep deploying model version 1 for now, because we see that the average reward is higher. Well, actually no, 18 divided by 8, 5 divided by 2. Well, actually we can see that it will probably start rolling out more and more model version 2, because the average reward for model number 2 is higher than the average reward for model number 1. And that is exactly what we wanted in the first place. We wanted a system for our model to be able to automatically pick which model is the best to deploy, right? And that's exactly what this hard memory is helping our agent to do. We've taken a first stab at this, so there's quite a lot of assumptions gotten into this and quite a lot of simplifications. The main important simplification that I want to draw your attention to is that here there is a lot of ways in which you can define this algorithm here. Our algorithm is very simple. Our algorithm just tells us, based on our exploration versus exploitation hunger, which action we should take. In fact, we're basically saying that the more actions you've taken already, the less you should do some exploration. And it kind of makes sense, right? When I've burned myself already the first time by touching a plate in the oven, what I don't want to do is touch it again, right? I just know that it's hot. So I've touched it, it's hot. I'm done with exploring this. I just know that it's hot. I don't want to touch it again. And that's exactly what we're going to do here. We're just saying hey, if you've already explored a lot and you've already taken a lot of actions and something doesn't give you a very high reward, don't keep exploring and playing this action. Just move on and just do more and more of the optimal action here. So that's one of the algorithm that we have explored, and it's actually called Epsilon Greedy. Now, there is a bunch of other algorithms that exist out there, from upper bounds to Thompson sampling, just a lot of different algorithms that allows our model to balance out the trade-off between exploration and exploitation as fast as it can, so that you minimize the regrets and you maximize the amount of reward that you accumulate throughout the lifetime of the system. All right, guys, that was the beginning of a very important topic. I hope that you enjoyed the discussion here, and I just wanted to remind you that there is a ton of content on this topic, and I'm going to add a few resources on the typical resource tracker so that you can keep exploring this topic.